You do one thing wrong every single day and you don't even know it. You look at your phone and think it's just a screen, a battery, some apps. You assume the real magic is in the processor or the camera. But the truth is, the part that actually keeps your digital life from falling apart, the one piece that stands between you and total radio chaos, is something you've never even heard of. In this episode, I'm going to walk you through 7 turning points that turned a forgotten radio problem from the 1950s into one of the most important invisible technologies in your pocket today. Point number 4 is the most uncomfortable because it shows how close we came to building a world that simply wouldn't work. Point number 7 will change how you think about your phone, your Wi-Fi, and every wireless standard you've ever used. And at the end, I'll give you a simple mental test, a way to look at any new gadget and instantly see whether it's built on solid engineering or just on clever marketing. Don't scroll away. Let this settle for a second. There is a component inside your smartphone that wasn't designed for smartphones at all. It was built by a small group of radio hobbyists in the 1950s, men and women sitting at crowded workbenches surrounded by coils, capacitors, and metal chassis, who never imagined a world with mobile apps, streaming video, or tap to pay. They had a painfully simple problem. Every voice transmission on shortwave was wasting half of the precious airwaves. An ordinary AM voice signal sent the same information twice. One copy of your voice above the carrier frequency, one copy below, both taking up bandwidth, like printing every book in duplicate just to be safe. On bands already packed with stations, that was brutal. If you were an amateur squeezed into a narrow slice of spectrum, the space your conversation took up wasn't just a luxury, it was the difference between getting through and being buried under your neighbors. Emotionally, this wasn't just a technical itch. Imagine 2 people on opposite sides of an ocean, a young student, a retired engineer, trying to make contact late at night through shortwave static. One of them has only a cheap transmitter. If their signal takes twice the space it really needs, they lose. Their voice literally disappears under stronger neighbors. That's the human cost of wasted bandwidth. The fix was brutally elegant. Engineers invented a technique called single sideband. Strip away the carrier, strip away one of the mirrored copies, transmit only the sideband that remains. Same conversation, half the space, with far more of the transmitter's power going into the part that actually carries the voice. It sounds like magic, but there was a catch, and it was hard. To keep just one sideband, you need a filter that passes the frequencies you want and violently rejects the ones sitting right next to them. For speech, the lowest useful audio tone is usually treated as about 300 Hz. That means your wanted and unwanted sidebands are separated by only about 600 Hz. In engineering terms, that's a very thin wall, and you're asking that wall to be almost perfectly vertical. Ordinary circuits built from coils and capacitors simply cannot cut anywhere near that steeply. They slope, they leak, they let unwanted frequencies bleed in. So the radio amateurs were stuck with a cruel demand. To build single sideband, they needed resonators with an extraordinarily high quality factor, Q, the measure of how cleanly something vibrates. This is the first turning point. In the 1950s, high Q meant one of 2 things: quartz crystals or precisely machined metal. Those weren't cheap parts you picked off a shelf. They were the product of decades of physics and craftsmanship, and they trace back to a discovery made in a Paris laboratory in 1880. 2 brothers, Pierre and Jacques Curie, showed that certain crystals, quartz among them, produce a small electric charge when you squeeze them and flex slightly when you apply a voltage. This 2-way relationship between an electrical signal and mechanical motion is called piezoelectricity, and it's the quiet thread that runs through this entire story. A slab of quartz, cut the right way, doesn't just conduct a signal. It vibrates at an incredibly stable, sharply defined frequency, like a tuning fork made of stone. That stability matters because the cleaner a resonator holds its frequency, the steeper the filter you can build around it. That is exactly the near vertical wall that single sideband demanded. Pause on that for a moment. You're talking about a piece of rock, shaped and cut, that becomes a kind of gatekeeper for human speech. One man turns on a radio in a cramped apartment. Another replies from a ship. Between them, a vibrating crystal decides what makes it through. By 1929, an engineer at Bell Laboratories named Warren Mason had figured out how to build those quartz crystals into full filter networks. The telephone company used them to stack 12 separate voice conversations onto a single pair of copper wires, each call in its own narrow slice of frequency, kept apart by crystal filters sharp enough that the conversations never bled into each other. That was the second turning point. Before the ham radio community ever picked up the idea, the core concept, using a vibrating piezoelectric crystal as an almost perfect frequency gatekeeper, was already proven in the heart of the telephone network. Emotionally, think of it this way. Somewhere in a switching office, a row of quartz slabs is quietly deciding which of 12 voices gets to use which slice of copper. It's like an invisible traffic system, with no traffic lights and no police, just crystals doing their job. By the late 1940s, single sideband moved out of those telephone labs and onto the amateur bands. Oswald Villard, an electrical engineering professor at Stanford, put the university's radio station on the air with a single sideband voice transmitter. In 1948, the amateur radio magazine QST began running a monthly column devoted entirely to the technique. It spread fast through the hobbyist community. In 1951, two contributors named Weaver and Brown published detailed crystal lattice filter designs in QST, showing ordinary amateurs how to select one sideband and reject the other using banks of quartz crystals wired onto a homemade metal chassis. This is where the story takes on a very human shape. You have people in garages and basements, not corporate labs, copying diagrams from a magazine. They're soldering crystal sockets onto tin sheets, tuning their home-built filters by ear and by oscilloscope. They're trying to push their single voice into a band full of noise without getting buried. I know what you might be thinking. Okay, that's quaint radio history. Interesting, but what does it have to do with the dense networks we use today? Here's why that reaction misses the key point. Once a community figures out how to take a fragile lab idea, piezoelectric crystals in carefully controlled conditions, and turn it into something you can actually build on a garage workbench, the technology isn't just proved, it's democratized. That shift is what allows it to seep into places the original inventors never expected. And that leads us to the third turning point. Quartz wasn't the only path to sharp filtering. A few years earlier, in 1946, an engineer at Zenith named Robert Adler built a filter that worked mechanically instead. Inside a metal tube, barely larger than a cigarette, he assembled a row of precisely ground metal discs, coupled so that the whole assembly resonated at 455 kilohertz and filtered the signal through physical vibration rather than through a crystal. That design caught the eye of Collins Radio, a company in Cedar Rapids, Iowa, founded by lifelong amateur Arthur Collins. In the early 1950s, Collins took Adler's mechanical filter into volume production. Their receiver, the Collins 75A4, released in 1955, became widely regarded as the first production single sideband amateur receiver using a plug-in mechanical filter to shape its passband. Paired with its matching transmitter, the set cost around $2,500, so expensive that hams nicknamed the pair the Gold Dust Twins. For most hobbyists, that price was out of reach, but in terms of technological history, it was crucial. The sharpest filters in radio had gone from lab curiosities to physical objects you could hold in your hand, swap in and out, sell, ship, and eventually bolt onto serious hardware. Then something predictable happened. The same filtering trick the amateurs had refined started flying on American bombers. After Collins gear was demonstrated aboard a Strategic Air Command aircraft in 1956, single sideband became standard for long-range military communication for roughly a decade. This is the emotional layer you rarely hear about. A technology born from hobbyists trying to make their voice heard through static ends up as the backbone of communication for bombers carrying nuclear weapons. Somewhere, a radio operator flips a switch, trusting that mechanical discs inside a metal cartridge will keep their lifeline clean. You can feel the stakes rising. But the sharpest filters in radio were still physical objects you could hold in your hand, quartz slabs in machined metal discs. That changed in 1965 when two researchers, Robert White and Fred Voltmer, introduced a device called the interdigital transducer. Instead of sending vibrations through the bulk of a crystal, they laid a set of interlocking metal electrodes, shaped like the fingers of two combs pushed together, onto the polished surface of a piezoelectric wafer. A signal applied to those electrodes launched a tiny acoustic wave that rippled across the surface. The spacing of the fingers decided exactly which frequencies survived the trip. This was the surface acoustic wave filter, and it could be manufactured in a new way, photographically printed onto a substrate, almost like a modern circuit printed onto a chip. That manufacturing shift mattered as much as the physics. A filter you can print by the thousand is cheap. And cheap is what eventually lets a technology slip into mass-market consumer devices. Think about the emotional translation. We've moved from handcrafted crystals and machined discs to thin films and printed fingers. You're no longer depending on one artisan grinding quartz. You're depending on a process that can stamp uniform pieces over and over. That's the seed of scale. Surface acoustic wave filters grew up first inside radar systems. Then they moved into television sets, replacing bulky tuned circuits in the picture and sound stages. The story loops back on itself here because Robert Adler, the same Zenith engineer who built the mechanical disc filter in 1946, was also an early pioneer of surface acoustic waves in television. One man's career directly connects the machined metal era to the printed chip era. By 1975, the Japanese component maker Murata had surface acoustic wave filters in mass production. Over the following 2 decades, they worked their way into cordless phones, pagers, and eventually the first cellular handsets. This is our fourth turning point, and it's the uncomfortable one. Once a technology becomes cheap and printable, it stops being special. It dissolves into the background. It turns into just another part, and you stop noticing how much depends on it. Next, we're going to push that idea forward into thin film bulk acoustic resonators, into billion-unit markets, and finally into the dense multi-radio smartphone you're probably watching this on right now. Don't fast forward. The real shock comes when you see how many of these filters live inside a single phone, and how they quietly keep your modern world from tearing itself apart. We left off at the moment when filters stopped being rare hardware and became printed patterns on a wafer. That's where technologies usually vanish from public memory, when they stop looking dramatic and start looking like just another chip. But that's exactly where the real consequences begin. Surface acoustic wave filters were perfect for the early generations of wireless. They handled the frequencies used by cordless phones, pagers, and first-generation mobile networks beautifully. A television set, a radar dish, a primitive cell tower, all of them could rely on those tiny surface ripples to keep picture and sound separated, to keep one channel from leaking into the next. Imagine a family in the 1980s sitting in a small living room. The TV is bulky, the remote is clunky, the picture quality is good enough. Inside the set, surface acoustic wave filters are quietly replacing the old bulky tuned circuits that used to require careful manual adjustment. No one in that room knows the term interdigital transducer. They just know that channel 3 no longer bleeds into channel 4. But as the wireless industry climbed to higher and higher frequency bands, the surface waves started to run out of room. Think of it like this. If your entire highway system is built for sedans, and suddenly you want to push high-speed trains through the same infrastructure, it doesn't matter how well the old asphalt was laid. The speed and power simply overwhelm it. Surface waves propagate along the material. They're limited by the geometry and the physics of the surface. Past a certain point, you need a new trick. That trick was to send the acoustic wave back down into the material, but this time, not through a chunky slab of quartz, and not just across the surface, but through an ultra-thin film. In 1993, research labs at Hewlett-Packard began developing what became the thin film bulk acoustic resonator, usually shortened to FBAR. The idea was deceptively simple. Stack a film of piezoelectric material, typically aluminum nitride, only a few thousandths of a millimeter thick, between two electrodes. Then let the sound wave bounce vertically through that film at frequencies far above anything a surface device could reach. This was the fifth turning point. When you shrink the vibrating element down to such tiny dimensions, you unlock whole new ranges of frequency. The same physical principles apply: piezoelectricity, resonance, Q factor, but the geometry lets you climb the spectrum ladder. Suddenly, you can build filters that sit comfortably in bands used by modern cellular systems. Second, third, and fourth generation, each with tighter requirements and more aggressive coexistence problems. Emotionally, this is the moment where the story feels almost science fiction. Inside a package, you need a microscope to inspect. A film that's thinner than a human hair is making yes-no decisions about radio energy that spans continents. By 2001, after the group at Hewlett-Packard had spun out into Agilent Technologies, they shipped the first commercial bulk acoustic wave duplexers for mobile phones. These parts were prized because they were dramatically smaller than the ceramic filters phones used at the time, and critically, they held up to more transmit power without distorting. As phones started pushing their signals harder to reach distant towers, that robustness mattered. I know what you might be thinking. All right, so the filters got smaller and better. That's progress. But does it really change the shape of the world? Here's why it does. When you make something both cheaper and more capable, you don't just improve existing devices. You enable entirely new classes of devices. A bulky filter means big phones, big radios, big boxes bolted to walls. A tiny, high-performance filter means sleek, pocket-sized, battery-powered universes. The technology scaled at a pace that's hard to visualize. By the middle of 2008, more than 1 billion bulk acoustic wave filters had been sold. Picture that number in human terms. 1 billion resonators means roughly one device for every person in China, or nearly one for every human in the Americas. That's not a niche, that's infrastructure. Every time a person in a remote village makes their first phone call, every time an office worker in New York taps their phone to join a conference, every time a parent in Nairobi checks a map to see where their child's bus is, somewhere in the chain of devices and towers, there is a tiny film of piezoelectric material bouncing a wave up and down and deciding which slice of the spectrum gets through clean. All of this traces back to the same piezoelectric effect the Curie brothers demonstrated in 1880, and the same sharp-skirted filtering the ham operators needed on crowded shortwave bands. Only now the whole thing has shrunk down so far that most people will never even glimpse it. This is the sixth turning point. The moment a once visible technology crosses the line of human perception. From that point on, you only hear about it when something breaks. Don't rush past this. When a component becomes invisible and omnipresent at the same time, it stops being a part and becomes a kind of quiet leverage point for the entire global system. Which brings us to your phone. A modern smartphone is not one radio. It's a dense cluster of them, all running at the same time. It handles second, third, fourth, and fifth generation cellular signals across dozens of separate frequency bands, plus Wi-Fi, Bluetooth, GPS, and the near-field chip that lets you tap to pay, all packed into a sealed case a few millimeters thick. Every one of those transmit and receive paths needs its own filter to pass its assigned band and reject everything else. If you don't separate them, the radios inside the phone drown one another out. Visualize it. You're standing in a busy train station. Your phone is streaming music over Wi-Fi, receiving a text over LTE, holding a Bluetooth connection to your earbuds, and pinging GPS satellites to keep your navigation updated. All of that is happening inside a tiny slab of glass and silicon in your hand. Now imagine every one of those signals as a crowd of strangers shouting in different languages. The only reason you hear the voice you care about, the podcast you're listening to, the person calling you, is that there are dozens of invisible gatekeepers separating each crowd, letting only the right words through to the right ears. Engineers call this the coexistence problem, and it has gotten harder with every generation of the network. A first-generation phone from the 1980s needed only one or two crude filters and couldn't even send a text message. Fourth-generation handsets built for worldwide roaming carried somewhere between 50 and 90 filters. Premium fifth-generation phones pushed that count toward 100. Part of the reason is that core fifth-generation bands are enormously wide, demanding several hundred megahertz of bandwidth, where a typical fourth-generation band needed only about 60. That's exactly the kind of job that favors bulk acoustic wave filters over the older surface type. Emotionally, this means that what looked like a neat historical story about crystals and ham radios is actually the skeleton under everything you do each day. Lose those filters and your smartphone becomes a confused brick. In late 2025, one major RF component maker put it bluntly. Today's premium smartphones contain nearly 100 filters, spanning everything from low-band cellular up to Wi-Fi. That demand has turned the humble filter into one of the most valuable and fought-over pieces of the entire wireless industry. A research firm valued the mobile radio frequency front-end market, the bundle of chips that includes these filters, at more than $15 billion in 2024, sitting inside a total RF market above $50 billion. Companies have been consolidating hard. Qualcomm bought out its filter joint venture with the Japanese firm TDK in 2019 for more than $1 billion. Broadcom still carries the original FBAR lineage, directly descended from that Hewlett-Packard project from 1993, and supplies filters for Apple. In late 2025, two of the largest American suppliers, Skyworks and Qorvo, announced a merger deal valued at roughly $22 billion. This is our seventh turning point. What began as a hobbyist struggle to fit one clear human voice into half the radio space it normally took up has become a cornerstone of a global industry worth tens of billions. The economic stakes around these invisible filters are huge, but the personal stakes are even bigger. Because the next time you make a call, or your phone quietly hands your data from one cell tower to the next without dropping the connection, it is worth remembering what is doing that work. Somewhere in that sealed glass case, a row of tiny piezoelectric resonators is performing almost exactly the same task a slab of quartz performed on a hobbyist workbench in 1955, passing the signal you want and rejecting the noise you don't. Take a breath here. The straight line from that garage filter to the 100 filter smartphone in your pocket is not obvious. But once you see it, you can't unsee it. We've just traced the backbone of how past technology, piezoelectric crystals, mechanical filters, surface waves, thin film bulk resonators, quietly built the future you live in. In the next part of this episode, I'm going to give you a free mental tool based on this story. A way to look at any shiny new wireless gadget and ask one simple question that instantly tells you whether it's built on solid engineering or just on marketing gloss. And only after that, I'll show you how all these pieces come together into a single system. The same pattern, applied to the way you make sense of complex tech around you. Stay with me. The most important part isn't the history, it's what you do with it. You've just seen how a forgotten problem on shortwave bands turned into one of the most critical invisible technologies in your phone. Let's turn that history into something you can actually use. Because every future technology you're going to see, every new wireless standard, next-gen router, smart device, stands on one simple question. Where is the hidden gatekeeper? That's your free tool. Whenever you hear about a new piece of tech that connects faster, talks to more devices, or uses less battery, stop for a second and ask, what is doing the job that those filters did on shortwave radio? Who is separating the useful signal from the noise? Who is keeping the channels from drowning each other? If you don't see a clear answer, be suspicious. Let's make this concrete. Imagine a couple in their 40s who just bought a smart home kit. It promises seamless Wi-Fi coverage, direct connections to light bulbs, thermostats, door locks, security cameras, plus a hub that talks to all of them at once. They plug it in. At first, everything feels magical. The living room lights respond to voice commands. The front door locks when they say it should. The heating turns on before they get home. Then slowly, problems start. The camera stream freezes when someone starts a video call. The door lock lags just long enough to be annoying. The thermostat app says, "Device offline," every few days. None of this looks catastrophic, but it adds up to something simple. The wireless environment is crowded, and nothing is really keeping the pieces apart. Now take your tool and apply it. Where is the hidden gatekeeper? If the marketing material talks about band steering, mesh networking, cloud intelligence, but never explains how the system keeps different radios from stepping on each other, you've found the hole. It's like building a city with high-speed cars and trains, but forgetting the signals and switches. This is more than just an engineer's concern. For that couple, the difference between a well-designed coexistence system and a lazy one is the difference between a home that feels safe and one that feels glitchy and unreliable. Here's the second part of the free tool. Always ask, what old problem is this new technology secretly solving? The ham radio filter was solving too much voice in too little spectrum. FBAR filters in smartphones are solving too many radios in too little space. When you hear about a new wireless standard, a new IoT platform, or a new satellite network, don't get stuck on the buzzwords. Look for the older problem hiding underneath. If the creators can't explain which past limitation they're beating, is it range, noise, interference, power, size? Then chances are they're not building a real future technology. They're just rearranging the present. Why does this matter emotionally? Because you, somewhere between 30 and 55, have already lived through enough tech hype cycles to know how it feels when a revolution quietly turns into clutter. Boxes that break, subscriptions that pile up, devices that die after 3 years. The free tool we're building here is a way to protect your time and money from that cycle. Don't scroll yet. We're about to connect this directly back to your phone and then zoom out to the bigger picture. Think back to the smartphone we talked about. Inside it, each filter is doing 2 jobs at once. It's defending one band from all the others, and it's making sure the device can share a crowded spectrum with strangers. That pattern, defend local, share global, shows up everywhere in future tech. A neighborhood Wi-Fi network does it when it lets your router talk cleanly while the cafe across the street blasts its own signal. A car-to-car communication system does it when your vehicle broadcasts its position without jamming emergency services. A medical implant does it when it sends data to a reader without interfering with your heart's own electrical rhythm. Your free tool is to spot that pattern. Every time you see a rectangle of glass and metal or a little plastic hub, try this. Ask, what is it defending? Ask, what is it sharing with strangers? Then ask, what is filtering those 2 worlds? If you can answer that, you're no longer just a user. You're someone who reads the infrastructure behind the interface. Now here's where most explanations stop, at the level of the aha moment. But that's only part of the system. Knowing that there's a hidden gatekeeper is powerful. Knowing that every future technology solves an old problem is powerful. You can already use these two questions to cut through a lot of hype. But if you want to really understand where we're going next, with denser networks, more devices, and more automation, you need a framework that ties everything together. A way to line up past, present, and future on one axis and see how they repeat. That's where what I'm building comes in. It's a full narrative lens for tech, a way to take stories like the ham radio filter, the bulk acoustic resonator, early TV circuits, and map them onto the gadgets and systems you're looking at today, so that you can say, this isn't just a cool device, it's chapter 3 of a story that started in 1929, or this isn't just an app, it's a thin layer on a foundation laid by some engineer whose name most people have forgotten. And yes, I've turned that lens into something more concrete. Here's the product mention, Patoyer formula. I've taken this entire pattern, the hidden gatekeepers, the old problems behind new hype, the way small lab discoveries turn into billion-unit infrastructure, and turned it into a structured guide for reading technology history forward, so you can spot which future systems are actually worth your attention and which ones are just noise. But before we get to that, remember, you already have a free, working solution. You have 2 questions you can use right now before buying your next device, subscribing to your next service, or believing the next revolution headline. Where is the hidden gatekeeper? What old problem is this really solving? These alone will save you from a lot of bad decisions. They're just one piece of a larger system that I've put together. A way to connect stories like this ham radio to smartphone journey with everyday choices about tech, from your home network to your car, your job, and even how you think about regulation and safety. Everything together, the full system, the examples, the step-by-step way to apply it, is in one place. The link is in the description, but stay, because what comes next is the most important part. We've spent most of this episode walking forward, from a crowded shortwave band in the 1950s to the inside of your smartphone today, from thick quartz slabs to films so thin you need a microscope to see them. Now I want you to flip the direction. Instead of asking, how did past technology make this possible? Ask, what happens if we take this logic and push it further, into the world we haven't built yet? Because the coexistence problem, too many signals in too little space, isn't going away. It's intensifying. Start with something simple, the street outside your home. Right now, it's probably bathed in a mix of Wi-Fi, cellular, Bluetooth, maybe some short-range industrial radios from nearby elevators, sensors, or security systems. It feels invisible. You don't see the traffic. But if you could, it would look like a swarm of colored threads. Blue bands for mobile data, green for Wi-Fi, faint yellow pulses from key fobs and door locks. Now imagine layering another system on top. Cars talking directly to each other to avoid collisions. Streetlights talking to a central controller to save energy. Air quality sensors texting numbers back to a server. Delivery drones pinging a guidance network as they move between buildings. Each new layer doesn't erase the old ones. It stacks on top. The future of technology, the kind you're interested in, the kind that only exists because older systems worked, is a future of denser stacks. And anything built on top of those stacks will live or die on the same quiet question. Who is filtering what? Take satellite constellations. We're already launching hundreds, even thousands of satellites to provide global internet coverage, remote sensing, navigation improvements. Some orbit low, some high, some send broad beams, some narrow. From the ground, your phone or your house antenna just sees a signal from above. But the truth is more crowded. Different constellations use different bands. Some overlap, some sit close. All of them have to coexist with weather radars, aviation systems, military networks. When an engineer designs a receiver for that environment, they're essentially faced with the same problem we saw in the 1950s. Separate what you need from what you don't, even when the frequency gap is painfully small. Inside that receiver, there will be gatekeepers, filters, resonators, clever signal processing algorithms, doing the same job the quartz slab did for 12 telephone calls on a copper pair. The physics hasn't changed, only the scale has. Emotionally, this matters because those invisible decisions will control who gets reliable coverage and who doesn't. Which regions can trust satellite data for agriculture, disaster response, navigation, and which regions get service that fails when the sky gets busy. Now zoom down again to something much closer, dense IoT environments. Picture a hospital 10 years from now. Every bed has sensors. Every monitor streams data. Every infusion pump talks to a central control system. Every staff member carries a badge that tracks their location. The building itself has temperature and humidity sensors embedded in walls, elevators, ceiling tiles. Every one of those devices relies on wireless links. Some use Wi-Fi, some use Bluetooth. Some talk to private cellular networks. Some use low-power protocols you've barely heard of. If that environment is designed with the filter logic in mind, with clear decisions about which band is for what, which signals get priority, where hardware filters protect critical channels, then the technology quietly helps the staff do their job. Nurses spend less time fighting network glitches. Doctors see data that actually reflects reality. Patients benefit. If it isn't, then interference becomes more than an annoyance. It becomes a safety issue. A sensor dropping its connection at the wrong moment, a pump that fails to receive a dosage change, a monitor that goes offline. Each of those looks like a small glitch on a dashboard, but underneath it's the same old story. No one thought seriously enough about how the signals would coexist. Your phone's 100 filters are a preview of that world. They're the training wheels. This is why I built the framework I mentioned earlier. Because once you see that the same pattern governs ham radios, telephone networks, bombers, TVs, smartphones, satellites, and hospitals, you can't just treat each gadget or platform as isolated. You start to see a continuum. You see that technology of the future is often just technology of the past, compressed and stacked a little tighter. And that changes how you make decisions. When a city proposes a new smart traffic system, you don't ask, is the app nice? You ask, what old filter problem is this solving? Where are the gatekeepers? When your employer rolls out a new set of collaboration tools that rely heavily on wireless connectivity, you don't just ask, does it sync across devices? You ask, what happens when everyone in this building tries to use it at once? Who is separating their signals? When you hear about a new consumer gadget promising seamless connectivity, you don't just ask, is it compatible with my phone? You ask, how does it behave in a crowded spectrum? What invisible infrastructure is it leaning on? This is the emotional payoff of our story. You move from being carried by technology to seeing the currents beneath it. The product I've linked, the full system, exists to help you do that systematically across more technologies than we can cover in a single episode. But even if you never click, you now have a mental lens that most people never develop. Let's close this with 3 concrete steps and the 3 elements you asked for in the finale. First, a specific question for the comments. Drop a number from 1 to 7 in the comments. Which turning point hit you hardest? Was it 1, the ham radio struggle with wasted bandwidth? 2, quartz in telephone offices? 3, mechanical gold dust filters? 4, printed surface waves? 5, ultra-thin bulk films? 6, the billion-unit explosion into phones? Or 7, the realization that these invisible parts now anchor a tens of billions market? Your number will tell me which part of the story you're most ready to dig deeper into. Second, a share request aimed at one person. Send this video to exactly one person you know who still thinks technology just appears. A friend who loves gadgets but never thinks about the infrastructure behind them. Or a colleague who complains about bad Wi-Fi without realizing what's actually happening in the air. One share from you might save them years of confusion and a lot of wasted money on devices that were never built to survive in crowded environments. Third, a hook for the next episode. Next week, I'll take this filter lens and aim it at a completely different system. The way early power grids decided who got reliable electricity, and a set of internal documents from the 1930s that show one thing very clearly. They knew that if they didn't build the invisible gatekeepers right, the whole system would fail. We'll look at how those decisions still affect the quality of your power today, and how the future of smart grids and vehicle-to-home systems is quietly repeating the same mistakes, unless someone learns from the past. Stay tuned.